Hi guys, welcome back to Data Every Day. Today we're looking at a data set of EEG brainwave data recorded from subjects while they were watching a series of 5 different movies, actually scenes from movies, and we're going to try to predict the emotional state of a given subject during a given movie. At the end of all these 2,500 columns, we have the label column with the values. So let's get into the notebook. So we're going to use a TensorFlow neural network to make our predictions, and we're going to use Matplotlib and Seaborn for visualization, NumPy and Pandas for working with the data, then the train test split function from sklearn for making our split, and TensorFlow to actually build our model. And then we're going to analyze the results with the confusion matrix and classification report from sklearn. So I'm going to go ahead and import that, and I'm going to read in the data using pandas.readcsv. We can get the CSV file right over there. I'm going to paste it in, and we'll take a look. So this one has 2,500 columns, and I definitely can't see all of them, so I'm going into the console and typing pandas.set option max columns none. And that will allow me to refresh the data frame, and I can see now all 2,500 columns. So we have quite a few columns. Now, from the looks of it, it seems to be some sort of time series data set. It's possible that each of these numbers represents a time step, and we have the maximum from each time step, or they represent different movies. It's not entirely clear, but we do have these FFT features that certainly do look like time series features because there are 750 of them. And it's important to note we have a whole half of the data set actually is consisting of A values, and then the second half all has B at the end. So if you look at the data set, what it says is it was taken from 2 people, 1 male, 1 female, for 3 minutes per state. So there's not a whole lot of information, and I was sort of digging around. I was unable to figure out what each of these columns means. Some of it is self-explanatory. For example, the means, well, I'm not entirely sure what is the means of. Mean D, and then you have mins, maxes, covariance matrix, correlations, log M, which I'm not sure exactly what it is. Then it repeats again. We also have eigenvectors or eigenvalues. So yeah, so what I'm going to do is I'm going to treat it like time series data, and I'm going to try to use like sequential processing methods in the model to try to see if that will improve the performance. So actually I should say we'll use a recurrent neural network to make our predictions. So let's take a look at a bit of the data. So as a graph, right? I'm going to get a sample. We're just going to take the first row of the data, and it's going to be data.loc all rows. No, actually, sorry, the first row, and let's just get the FFT readings, which I'm not entirely sure what it means, but it's the one that I'm most confident is time series data. So I'm going to get the first one, which is actually FFT0B to FFT749B. And then we're going to plot it. So make a new matplotlib figure, maybe with a fig size of 16 by 10. And right, so let's plot our sample with plt.plot. On the x-axis, I'm going to have a range, which is of length of the sample. And on the y, I'm going to have the sample itself. Let's just give it a title. Features FFT underscore B underscore 0 underscore B through FFT 749 underscore B. So it does look like time series data, right? This looks like an EEG rating. So I can't be absolutely sure, but I'm I assume that there is some amount of time series data in here. So let's look at the class distribution. So I'm going to get just the label column on the end, right? And I'm going to get the value counts for it. So this will show how many of each value we have inside the column. And you can see it's very fairly balanced, maybe a slightly more neutral values, but that's fine. This is almost a 1/3, 1/3, 1/3 split, so we don't have to worry about imbalanced classes. And let's create a label mapping. So I want to make a dictionary that's going to map each of these values to an integer. So we have negative, which we can map to 0, neutral, which we can map to 1, and positive, which we can map to 2. Now, I'm going to start pre-processing. So I'm going to make a function called pre-process inputs. It's going to take in a data frame. It's going to make a copy of the data frame. Then it's going to split the label column off of the data frame. And it's going to, right, so this is the split happening. I'm dropping it from axis 1, storing that in x, and then I'm storing the actual column in y. And then it's going to return x and y. So this is sort of like a little function. We'll just pass our data frame in, and we'll get our process data at the bottom. It's nice to do this because you get to retain the original copy of your data, and then have a new copy at the bottom which you can customize in any way you want. And I'm also going to do the train test split inside here. So we're going to create four sets of the data: x train, x test, y train, and y test. And we're going to use the train test split function from sklearn to accomplish this, and pass in x and y, specify a train size of 70%, and this function will also shuffle the data for us. So I'm going to include a random state, which will ensure that the shuffle and the split is always performed the same way. And instead of returning x and y, I'm going to return x train, x test, y train, and y test. So down here I'll actually get the values from the function. And that's from pre-process inputs. Passing in data now. So if we take a look at this, we should have an x train that's just everything except the label column. It's been taken off, and this is 70% of the data. So it's pretty much ready to get fed into the model. Now normally I would scale the data, but it turns out, and this is from me testing it out before, scaling actually hurts the performance of the model. And it's sort of understandable, because if you think about what this data is, I can't speak for all of it because there's not too much information about what the features are, but let's assume that this is time series data based on this plot we have. What happens if we scale time series data feature by feature? Well, what that means is each column will now have a mean of 0 and a variance of 1 if we apply standardizing. But the problem then is each of these values gets changed relative to the other values in the column. But what's important about time series data is not treating each value as an independent feature. Rather, how does it relate to the other features? Like, what's the relative difference from one time step to the next, right? And so if we scale feature by feature, we're actually losing a bit of that relativity between examples. Between time steps. So in this case, it seems like scaling actually hurts. But if we are given a little more information about what this is, what part of it is time series, what part of it isn't, then we might be able to scale only those parts that are not time series data, and maybe employ some more advanced techniques as well. However, we don't have a lot of information, so I'm just not going to apply scaling. And it's sort of naive, but I'm going to treat the whole data as a time series. You'll notice if I do try to plot the whole data set as a time series, so if I do, instead of this, I do all columns. Oh wait, what's going on? Oh, the length. Wait, no. What's going on? Oh, I have to make sure not to get the label column. So just the last one. Right, so if I try to plot the whole data, you'll see it's bogus because we have these looks like almost 2 values, and it's hard to say how many these are. And it seems like it's 1 at the start. Maybe these are the max values because the maxes appear sort of near the start of each set. But remember, there's this A set and then this B set, and these guys are throwing off the scale completely. So it's clear that this is not one continuous time series. So we're going to proceed with the naive assumption that it is one continuous time series, just for the purposes of the video. But it probably warrants some further investigation. So I'm going to start building the model. Yeah, let me just keep this on here. Okay, so let's first try this with just a regular neural network. By regular, I mean 2 hidden layers, 64 activations apiece, just very standard. We'll have our inputs layer, which will be tf.keras.layers.input with a shape of, it's going to be xtrain.shape sub 1. So xtrain.shape, if we take a look at what that looks like, is 1492 by 2548. And so if we just index at 1, we will get just the number of features. So this is the length of a single feature vector coming in. And then, we'll create 2 hidden layers. We'll have a dense layer with 64 activations. It doesn't really matter. You'll see what happens. We pass in inputs. And again, here we're going to pass in x. Here's our outputs, tf.keras.layers.dense. And there's 3 activations here. That's because there are 3 different classes. So this is going to be, each one is a probability value for each class. So this is going to have a softmax function, which will just give each one of these a probability value such that they all sum to 1. So we're going to pass x in here and then create our model, which will be tf.keras.model, and passing in inputs as inputs, and the outputs will be our outputs layer. And we'll just print a summary of the model as well. And we have a problem. Activation, not activations. Alright, so we just have 3 sets of weights, actually 4 sets of weights between each layer. And so let's see what happens when we try using this model architecture to train. So I'm going to compile the model using an Atom optimizer. And we're going to use sparse categorical cross-entropy loss, which is best suited for multi-class classification problems like this. And for metrics, we'll just use accuracy. It's fairly decent metric to use since there's no class imbalance. And then let's train the model and store its results in history. So model.fit, training on xtrain, ytrain. Give it a validation split of 20%, batch size of 32, epochs. Let's train for 50 epochs and then employ the early stopping callback. So tf.keras.callbacks.early stopping will allow the model to take a look at the validation loss. We specify that here after each epoch, and it'll evaluate if the it'll check if the loss is improving, and if it doesn't improve for a specified number of epochs, let's say 5, then we'll stop the training and restore the weights from the best epoch. Alright, so I'm run that. And we have a problem. Oh yeah, okay, we forgot to actually convert these into numeric labels. So in here, before I make the split, we'll just take the label column and replace the values in it with the label mapping that we specified. So label mapping is up here, right? And you can actually just pass a dictionary into this replace function, and it'll automatically apply the mapping for each class. So that's going to be label. Now we'll run this down again and train. Alright, so it's training very quickly, and you'll see that the best loss we got, something around here, right? I'm not sure exactly, but let's see how it performed. So let's get the results, and I'm going to create a function called evaluate model. Actually, I won't make a function. We will just get the accuracy. So model ac is going to be model.evaluate on the test set. So we're going to compare the predictions from xtest to our actual values ytest. And I'm just going to turn off verbose mode. And we will get only the second value it returns, so sub1, because it returns the loss and the accuracy, and we just want the accuracy. So I'm going to print out test accuracy, and we can format it to 3 decimal places. Pass in model ac, and I'm going to multiply by 100 so we can get it in a percentage form. So I'm also going to put a percent sign there. And we're ending up with a test accuracy of 53%. So that is terrible. We can do so much better. So the reason this is not doing well is because it's treating each feature, each individual data point, as its own separate input. There is no concept of how they're related to each other. And an EEG reading is a time series. It's a collecting data over time, and what's most important about it is how it changes from one moment to the next. So with our current setup, with this just this 2 hidden layer setup, we're not able to capture time dependency in the data. So what I'm going to do instead is use a recurrent neural network. So recurrent neural network will pass in the data one bit at a time, and it's also going to take into account the last bit it saw. By bit here I just mean time step. So before I actually go and implement it, I also want to get a confusion matrix and classification report for the model. So CM will be our confusion matrix, and we can get it with the sklearn confusion matrix. We need some predictions before we can calculate it. So ypred will be our predictions, and we get that from model.predict on the test set. So this will actually return the output of the model, which if you look is actually 3 probability values, so not actually a classification. We can get the classification by doing the following. So if let's say we have a list of 3 probability values, 0.12, 0.33, no, I'll do 0.74, and 0.22. Okay, so let's say we want to get this represents class 0, class 1, class 2. Yes, I know it doesn't sum to 1, but don't worry about that. We can use numpy.max to get the largest number, and we can use numpy.argmax to get the location of the largest number. And if our classes are in this this setup, if each probability value represents a class, then by getting the argmax, we're actually getting the class which has the highest probability, and therefore our classification. So here, I'm going to take these 3 probability values, and I'm going to get the argmax of those 3. So this will return a bunch of different sets of 3 probability values. So I'm going to map a lambda function to it. It takes an x and returns numpy.argmax of x. And I'm mapping that to the predictions. So this will return the classification. Then let's turn that into a list, and once we've done that, we'll turn it into a NumPy array. Alright, now let's just take a look at what it looks like. You can see it actually gives us back classification values for class 2, class 0, class 1, whereas if we only did the model.predict, you can see that would give us a bunch of different sets of oh wow, this is so interesting. it's actually giving the, I mean, this still works, but I thought this gave probability values, not ones and zeros. This is, yeah, it's interesting. I wasn't aware of this. I thought it would give like 0.33, 0.33, 0.33 or something. Well, good to know. So anyway, yeah, so YPred is going to be not like this, which is like this one-hot encoded version of the classifications, but instead actually the actual integer classifications, which is what confusion matrix requires. As far as I'm aware, I don't think you can pass in one-hot versions. Alright, so ytest ypred, and then our classification report is from sklearn as well. That also takes ytest ypred, and we'll also give it some target names, which will just be the label mapping dot keys. So if you look at the label mapping again, you'll see this is our dictionary that maps a key to a value, and so if we just get the keys from it using dot keys, we'll get a list of the labels, the actual target names. So we can specify that in the classification report to have it show up as the right names. Alright, so now let's create a new matplotlib figure. I'm going to use Seaborn to visualize the confusion matrix. So figure size 8x8, sns.heatmap to get a heat map for the confusion matrix, which I'm passing in. Turning on annotations, I'm going to format it. First, actually, let me just set the minimum value to 0. Then I'm going to format it like so. This will ensure that the counts for the classifications don't show up as in scientific notation. Turning off the color bar, and I'm going to give it a CMap, color map of blues. Alright, then we'll give it some X ticks. So on the ticks are like the axis marks. And here, why don't I just plot it first so I can explain what it's doing. So this is our current confusion matrix. Currently it says 0, 1, and 2. I want it to say negative, neutral, and positive. So I can adjust the X ticks here. First I have to pass in a spacing that I want. So I'm going to use a numpy.arange, which will give an evenly spaced range from 0 to 2. However, this will be 0, this would be 1, this would be 2 in terms of spacing. So I have to add 0.5 to shift it into the middle like these ones are already. So that's our spacing, and then we're going to give the actual values, which will be given. We could type negative, neutral, positive, but we can also just get it from label mapping.keys. Okay, and then we're going to do exactly the same thing for the y ticks. So I'll change that to y. Then let's give the x label, which is the axis label, predicted, and the y label to we'll set to actual. Then we will give it a title, confusion matrix, and we'll show it. So now it's much nicer. You can see the actual classes and the classifications within each class. And then after that, I'm just going to print out a classification report too. So I'm going to copy this in. So basically, CLR, that's our classification report that we generated. I'm just printing a little header at the beginning so that we can see it like this. So, like I said, this model is not doing well. It's predicting so many as positive when it shouldn't. It's hardly getting any of the neutrals correct, and the negatives, it's doing okay in terms of negatives, but it's really confusing the neutrals and positives. So what can we do? Like I said, we're going to use a recurrent neural network. And so instead of these two dense layers, I'm going to use a gated recurrent unit. And let me see if I can explain this a little. Okay, so here is a graphical representation of a gated recurrent unit on the right. Now, a gated recurrent unit is a simplified version of an LSTM. However, even though it's simplified, it's perhaps more easy to understand what an LSTM does. So I'll start with LSTM. you'll notice first thing to notice about it is that it has this CT. This is a value, essentially. It's a vector that's getting passed through, and HT. And so the CT is called the cell state. The cell state runs straight through with only two operations applied to it. A multiplication, so this is pointwise multiplication, and pointwise addition. So essentially we're scaling it by some amount and then adding some value to it. It's important to note the HT, this is called the hidden state, is actually just a copy of the cell state. As you can see, it splits off, it copies itself, with a tanh function applied and some pointwise multiplication as well. So the cell state only has two operations for each pass, and the hidden state is just a copy of that with a few more operations added on. Now, what makes this a recurrent neural network is that after each pass, this cell state loops back around and gets fed back into itself. And the hidden state does a similar thing. It loops back around and gets fed back into itself. And so we're going to pass in time step by time step from the time series. And each time, it's going to take in the time step data, which is this. This is the new data. But it's going to take it in along with the data from the last time step. And it's not... The thing about these states is that they aren't exactly... You're not just passing in the last bit of data. You're passing in a sort of collection of information about all the data that the LSTM has seen. Because these orange boxes here actually have weights in them that are getting tuned as the model is training. So it's over time learning how to effectively store information about the whole time series, about the whole past, with each new bit of information that comes through. So I'll try to break down what each of these is. So this one is probably the simplest to understand. This is a sigmoid activation. So there's some weights here and a sigmoid activation as this passes through. So what sigmoid is it outputs values between 0 and 1. So if you think about a vector multiplication, so the cell state is sort of like, it's like the main memory of the LSTM. It's constantly being updated, but it always just feeds back through with these same two operations being applied. So this is sort of like, this contains the most long-term information, I would say. So if you think about a sigmoid activated vector being multiplied with the cell state, each value in the vector can take a value from 0 to 1. And if we're multiplying any number with 0 or 1, or any value in between, that's essentially it's saying, let's take something away. Because you're multiplying with a decimal value. Either we're multiplying with 1, which means keep it the same, times 1, keep it the same, or we're multiplying with 0, which means delete it completely, or something in between. But this is known as the forget gate, because we're actually forgetting a bit of the cell state, and how much we forget is determined by the weights, by the actual training. Then this is an addition. So after we've forgotten something, and you'll notice that what we forget is also basically depending on the previous hidden state, right? So the hidden state comes in, and then some amount of it is, it's scaled by a sigmoid function is applied, and then that's used to actually forget something. But then now this one with the plus, we're adding something back. And so this is also dependent on the cell state. Now, this is also a sigmoid activation, and it's being applied to a tanh activation. So let's start with the tanh. Here comes the hidden state, and it copies itself up here, and a tanh scale multiplies, it outputs values between 1 and -1. So it's sort of like it's almost like a directional scaling, right? But then that tanh is multiplied with a sigmoid. So in the end, it is it's sort of hard. It's a bit complicated. Basically, the way to think about this, I think, is you're taking some combination of the hidden state and adding it back into the cell state. So it's almost like a remembering gate, right? So we forget something, then we remember something, or we learn something new, and then we continue on into the next iteration. Before we loop back around, we send one more copy of the cell state to the final output, which has a pointwise tanh applied, and some amount of it is then again forgotten by this sigmoid. So it's a lot to wrap your head around, but basically the gated recurrent unit on the right here is a simpler version. It has only one hidden state, no cell state, and it also has a forget and a remember, or gain new information, right? So if you want to take a look, pause the video and try to figure this out or research it on your own, go ahead. I don't think I'm going to go into how it works because it's a little more mind-numbing, but it is simpler because it has fewer weights and because it only has one hidden state, but the concept is the same. Now GRUs tend to perform better on smaller data sets. In most cases you'll get a better performance out of a GRU than an LSTM, but not always. I'm going to use a GRU here. So we get that with tf.keras.layers.gru, and we specify some number of units to use. I'll use 256. This is a lot like just a dense layer. There's weights between the inputs and the units, so you'll have those weights, and then you get these 256 values. And then we're going to have return sequences. So this option, if we keep it off by default, look at this, right? This will run through a whole bunch of times for all of our time series data, and at the end it will finally spit out a final output, right? So if we have return sequences on false, all this will do is return that final vector output. But if we turn it on true, it won't only spit out the final output, but it will actually spit out the output from each time step, sort of stacked into an array. So all the different outputs. And this often improves performance. It has more data, obviously. So usually, by keeping return sequences on, we can get more performance out of the model. However, because now it's outputting a two-dimensional array, we're going to have to flatten it afterwards. So tf.keras.layers.flatten will convert the two-dimensional array into, stacking it into a long one-dimensional vector. So I'm going to pass in the output from GRU into the flatten, and I'll pass the output from flatten into the outputs. Now there's one more thing I should note. GRU layer requires the input to be three-dimensional. And the reason for that is because often each bit of data that comes in is encoded as a vector itself, so it needs a third dimension. So all we're going to do to compensate for that is get an expand dims layer, which is really just a TensorFlow operation, tf.expanddims, which takes in the inputs here, and it's going to expand the dimensions along axis 2, which gives it an extra dimension in the third or depth dimension. And now it can be safely passed into GRU. So let's pass in expand dims here, and then pass GRU into here, flatten into here, and finally we have our outputs. So if I run this, you can take a look at how it's doing. We have the initial input. We expand the dimension into the third dimension. We pass that into the GRU, so that you can see we have 256 units in the GRU for each of our examples. And then the output of that gets stacked on top for all the sequences, and then sort of concatenated together or flattened out into one dimension. and then that gets fed to our final output, in which is 3 values. So, right, let us now train and see how the model's performance varies. So we had a 53% accuracy before, and we're going to see how this one goes now. I think, okay, so GRUs do actually take a bit of time to train. Let's see how fast this one's going. We may want to turn on GPU acceleration. Yeah, it's going very slow, so I'm going to pause that, and I'm going to turn on GPU acceleration, and I will resume the video when we get back here. Alright, we are training again, and you can see right away we've already beaten the accuracy, at least the validation is saying we did, on the first epoch. So this architecture is completely changing the results we're getting. Because now the model is not only taking in each value as an independent value, but it's considering each value with a memory of all the others. So, you know, even if not all of this is time series data, it's okay to use the GRU here, because it's still sort of remembering these little, like, facts about the data. So yeah, I would like to know more about the data set, though, and what parts of it are time series, or if all of it is. So let's see, what's this validation loss? Oh, I think it has finished. Let's see how it goes. 95.9% accuracy. So if we look at the confusion matrix and the classification report, we have almost perfect performance. This is fantastic. We went from doing not much better than a random guess to almost perfect. Look, we have, let's take a look. So these are our true positives, or you could say, well, you can't really say true positives is best used, that terminology is best used for a binary classification when you have a positive and negative class. In this case, we'll say true negatives, true neutrals, and true positives, but I'm really referring to the class labels. So these are all the negative values that we predicted correctly. These are all the neutral values that we predicted correctly, and these are all the positive values that we predicted correctly. And you can see, so these are our predicted values on the x, and our actual values on the y. Out of all of the values we predicted positive, which are all these 3 squares, you can see we have a large number of them here, and that's actually given by the precision value for positive, which is 91%, or 0.91, which is saying out of all of these values, we got 91% of them correct. Then the recall for a positive is saying out of all the actual positives, we got 98% correct. And so the F1 score is a combination of the two, and we did perform very well in the positive class, even though that actually was our weakest class. If we look at the neutrals, we have out of all of our positively predicted neutrals, neutrally, out of all of our neutral predictions, it says we got 100% correct, but not really. The reason for this is we got 227 out of 228 correct, which is 99.56, which gets rounded up to 100. So that's why we're seeing 1.0 here. But we did extremely well, almost perfect. And in the recall for neutral, that's out of all the actual neutrals, how many we got correct? 98%. Also extremely good. So the F1 score, a combination of the two, is 99. Then we have the negative values, which is our final class here. The precision for the negative, that's of all of our predicted negatives, we got 98% of them correct. And the recall, out of all the actual negatives, we got 92% of them correct. And the F1 score is 0.95. So that will conclude today's video. Thank you so much for watching. I hope you enjoyed. If you did, make sure to subscribe and hit the bell for more content. And leave any comments you have in the section below. So I would like to say I did start a Patreon, so if any one of you would like to support me in any way, I'm going to leave the link in the description. And thank you so much for watching. I'll see you guys tomorrow. Have a fantastic day.